All right, so this is college algebra. Wanted a couple of announcements at the beginning here. First of all, your first web assigned homework is due tomorrow, the 30th of January. The first couple of sections, 2.5 and 2.6, I believe. And from what I remember, the last time I went through the web assigned grade book, which is just a day or two ago, a decent number of you, most of you probably, have gotten those two assignments done and have proceeded on to the next. So I think we're doing well there. So that's a good thing. Make sure that you know that your next assignment is due February the 4th, and that they're going to be due. You're going to have a couple of assignments probably due almost just about every week for the rest of the semester. So be looking for due dates on a weekly basis pretty much the rest of the semester. Exam 1, okay, a couple of announcements on Exam 1. First of all, the review for Exam 1 will be posted today. I did finish it over the weekend. I just haven't posted it yet, but I will put it up on your Google site this morning sometime right after class, right after this live lecture. And look for that. At the bottom of the Google site, there's a section there for exam reviews, so be looking for that. On-campus hours, as we move into Exam 1, I will be on campus February the 7th and February the 8th, next Wednesday and Thursday. On February the 7th, I'm planning 4 to 6 p.m. and February the 8th, 9 to 11 a.m. So I will be on the North Harris campus. Winship 115K is my office number, and please don't hesitate to come by if you have questions. It's never a bad idea to shoot me a quick message to let me know that you're actually planning on coming in, but you don't really need to make an appointment because I will be there during those hours. And then your testing window opens February the 8th and runs through the 13th. Tests are paper and pencil tests. Remember, it's not web assigned, there's no multiple choice, nothing like that. It's a paper and pencil, very traditional looking test. And the review will be a good practice for that. Also, while I'm talking about that, the practice problems for inequality. So let me kind of squeeze that in here. Inequality practice problems. The key to that will go up today also, probably not this morning, but sometime later today. So I sent everybody that assignment last week, and those are practice problems on inequalities, rational and quadratic inequalities. And I told you I wasn't going to pick that up, but that I would post the solutions to that so you could look at the problems. And I included that in Exam 1 because that's probably a good review for Exam 1 also. So it's a good thing to be looking at, definitely. And then today we're going to be going into Chapter 3. Today we're starting talking about functions. So I would say that today is going to be everything that we do now for 80 to 90% of the rest of the semester is going to have to do with functions in one way or another. So this is a big topic today. It's a big introduction. It's very important that you have an understanding of the definition of a function and basic things about functions as we go through the rest of the semester. Before I do anything else, does anybody have any questions that they want to ask? Those of you who are with me live today, anybody have any questions that they want to ask about?
No.
No.
All right.
I'm good.
Okay, then we are going to get started. Now, some of you will have seen some of this. Some of you who are with me from intermediate algebra will have seen some of this lecture before from last semester when we introduced functions in intermediate algebra. In intermediate algebra, we do a quick introduction to functions and then do some basic things with functions, but don't do a whole lot more else with that. Today, we'll use that same introduction that we did last semester, but we are going to go a lot further with it in college algebra than we ever did in intermediate algebra. And so first of all, so our topic for the day is functions. All right, that's what we're talking about, dealing with here. So before I deal with that word in particular, let's first talk about a relation and what a relation is. And then after we do that, And after we look at that very briefly, then we will talk about what a function is. So a relation is simply any correspondence between two sets. It's a really loosey-goosey, it's a very informal or a very general definition. It's just any correspondence that exists between two sets. That's it. The two sets are called the domain and the range. If I could spell domain, that would be good. So domain and range. And when I say it's any correspondence, you could say it's any relationship between these two sets, any way of getting elements from the domain to correspond to elements of the range. This is usually written as a set of ordered pairs. So when you write a set of ordered pairs, the x values typically make up, if you have this ordered pair, the x values are the domain values, and the y values are the range values. And because a relation is any correspondence that exists between two sets frequently, you'll see a relation, this word right here, defined simply as any set of ordered pairs. It's that simple. Any set of ordered pairs constitutes a relation. Right? So, for example, if I just do the ordered pairs 2, 3, 5, 6, 9, 11, 15, negative 4, 9, 27, 2, 16, something like that, that would constitute a relation, because it's just a set of ordered pairs is all it is, where the domain values would be 2, 5, 9, 15, and then I have 9 and 2 there again, and so I wouldn't list them. So the domain is just 2, 5, 9, and 15, and the range is simply 3, 6, 11, negative 4, 27, and 16. Right? That would be a relation. No big deal. It's really simple. It's any set of ordered pairs. A set of ordered pairs doesn't have to be numbers, right? It could be anything. So it could be people, or it could be people. Let's say people and colors, or something like that. So you might have Bob and Green, and Tim and orange, and Mary and purple. Right? That would be a perfectly good relation where you've got the domain as Bob, Tim, and Mary, and the range is green, orange, and purple. So a relation is a really general definition. Relations are frequently written out with graphs. So when you write a relation with a graph, you're frequently talking about an infinite set of ordered pairs. So, for example, that graph right there, even though I want to make sure you're careful here, it looks like it only has two ordered pairs on it. That relation actually has an infinite set of ordered pairs on it, because every point on that graph represents another ordered pair. And so there's actually an infinite set of ordered pairs there. So it's an infinite set of ordered pairs. And it constitutes a relation because it's a set of ordered pairs, right? Now there's a couple of these that are easy to identify. So like you've got 1, 1 is easy to identify, and 5, 3 is easy to identify because I've got them plotted there, but there's actually an infinite set of ordered pairs. Now, if you look back at the couple examples I've put of relations at the bottom of the screen here, right? These were ordered pairs, and we were just writing out the domain, just listing the domain values and the range values. Here we couldn't just list them necessarily. We would have to write them out in interval notation. And so the way I usually describe this to students, and some of you may remember this from last semester in intermediate algebra, is I just describe this when you've got a graph and you're trying to write the domain and the range, is I say just picture yourself. First of all, remember the domains live on the x-axis, right? The domains are the x's. The ranges live on the y-axis. So picture yourself walking along the x-axis, always from left to right. So you're walking along the x-axis, and you're looking vertically above and below, like that, as you're walking along. And if you can see the graph vertically above you or below you as you're walking along the x-axis, then that x value that you're standing on is in the domain. So the domain in this particular problem, as you move along the x-axis, would actually start here at x equals 1. That would be the first value that you see. And you would continue, as you walk along here, you're going to continue to see the graph. So let's say that's you standing there, right? You're going to see the graph right there. You're going to see the graph right here. You're going to see the graph in all those x values until you get to 5. So the domain in this particular graph are all the x's from 1 to 5. And if you think about the interval notation and the intervals we were talking about with inequalities last week, we could use the interval notation really nicely to write this out, that the domain is every x value from 1 to 5 and everything in between. So we could actually write it out in interval notation, bracket 1 to 5, and then close the brackets. Now you do the exact same thing with the range, except with the range, hold on real quick, the range you would picture yourself not walking along the x-axis, but climbing the y-axis. So here you are, climbing up the y-axis. So you're going from bottom to top. Remember, with domains, you're always going from left to right. So with ranges, you're always going from bottom to top. And here you're climbing the y-axis, and you're looking left and right in this case, and then you're saying, well, at which particular y values can I actually see the graph as I look to the left and to the right? And so the first y value you see here is at y equals 1, and then the last y value you see would be here at y equals 3, right? Every y value between 1 and 3 you'd see on the graph. And so the range on this problem for this particular graph would be all the y values from 1 to 3 with brackets around the 1 and 3 like that, because 1 and 3 would actually be part of the range. And so those are the domain and the range for this particular graph. And remember, this graph represents a relation, right? A set of ordered pairs. Now, remember what I said on the last page, that relations are any set of ordered pairs, right? There's no conditions that have to be met in order for a set of ordered pairs to be a relation. So this particular graph that I'm sketching right here is just as much of a relation as the one above. So let's say I have this particular graph like this, and it's a circle. Now we'll talk a little bit about circles later in the semester, but so that circle, and again, it looks like I've got just 4 ordered pairs on that circle, but there's actually an infinite set of ordered pairs on that circle. I've got 4 of them plotted there, but there's actually an infinite set of ordered pairs there, right? So that circle constitutes a relation. It's a relationship between 2 sets, the domain and the range, and the ordered pairs kind of tell you how that relationship works, or the graph tells you how that relationship works. Now, in this case, the domain, and remember the domains live on the x-axis. And so as you walk along the x-axis, remember that's what you're doing here, is you're walking along the x-axis from left to right. The first domain value, the first x value where you actually see the graph is right here at 2. And then the last place you see the graph is at that x value 6. And so the domain for this particular relation would be every x value from 2 to 6. And so this would be our domain. Bracket 2 to 6 and then close the brackets. And then the range, try to do this in a different color so it looks different. The range, remember you are climbing up the y-axis. So you're climbing up the y-axis like this and you're going from bottom to top. And the first y value where you see the graph is here at 1, right? That's the first place you see the graph, to the left or to the right. And then the last place you see it is here at 5. And so the range here would be from 1 to 5, all the y values from 1 to 5, brackets on the 1 and the 5 like that. Notice that there's no restrictions on what the x and y values are and how they relate to each other at all. So there's no big deal that, for example, you've got this ordered pair here 4, 1, and this ordered pair here 4, 5. That 4 value, the 4 is a domain value, and it gets related to, or it corresponds to, 2 y values, 1 and 5 both, and that's not a big deal. A relation is any set of ordered pairs. It's any correspondence between these two sets. And so that's just as much a relation as the first graph is. Now a function is a relation also. But so let's start off this right away to say a function is a special type of relation. Right, so it's a relation also, but it's a relation that meets certain conditions. So we put some restrictions on the relation, and then sometimes we get a function if it satisfies these restrictions. So what I'm going to do is I'm going to write this definition down, and then we're going to go through and kind of pick the definition apart and see what exactly it means. How does a relation get to be a function? Right, that's what we're talking about here. So a function is a relation where every domain corresponds to exactly one range. Right? A function is a relation where every domain value, so every domain value must be assigned to something, and it must correspond, or it must be assigned to exactly one range, like that. Every domain gets assigned to something, every domain gets assigned to something, to exactly one thing. Right? That's the definition for a function. Right? And so what we need to do is talk about exactly what that means and what its ramifications are, and what relations are functions and what relations are not functions. So what we're going to do is we're going to make up an example. And so our first example here is, what we're going to do is we're going to start off with two sets, a domain and a range. And what I'm going to do is I'm going to give you several different ways that these domain and range correspond to each other, and then we're going to pick out which ones are functions and which ones are not functions. They're just relations, but not a function. Okay? And we're going to start off with some what you might call somewhat non-traditional examples. They're just as mathematical as anything else. They're just not sets of numbers is all the difference is. But the domain, let's say, is the set of all people, let's see, set of all people in this class. And then okay, so that's everybody here. It's not just those of you who are listening to me live right now, but it's everybody who's going to listen to this who is actually enrolled in the class. And then the range is going to be the set of makes of car, makes of automobile. Now the domain then is everybody in this room, right? And when I say this room, it's my WebEx room and then all the other people that are in the class. And so, we could, I'm not going to identify anybody by last name certainly, but the domain is going to be Ashante and Charlotte and Cynthia and etc. Right? I'm not gonna list everybody who's listening to me live right now, but those people constitute the domain, and then the range would be the set of makes of car, and that's a long list. I'm just gonna write down some typical examples. So we could say Ford and Chevy and Toyota and Honda and VW, etc. Right? Those are examples of makes of automobile. And so, if we're going to talk about relations between these two sets, right, or a correspondence between these two sets, we have to have some way of assigning elements from the domain to the range. And that assignment procedure, we might call it a rule. We need a rule that tells us how to assign domain elements to range elements. And then what we want to do is look and see whether that rule that we make up is actually meets the definition for a function. All right, so our rule, and this would be rule 1. We'll look at several rules and see if they satisfy the definition for a function. So rule 1 is everyone. Now envision this as being an actual classroom, by the way. So let's envision ourselves as all being on campus right now, together in a classroom. That's the way this rule makes the most sense, even though we're doing this online right now. Everyone is assigned the make of car in which they arrived on campus. In which they arrived on campus today. And again, let's just pretend that we all came to campus, the same campus, and we're in the same room right now. All right, so if we think about that as being the rule, then everybody gets. So for example, this morning, I drove to campus, and so that's my name is the domain element, because right, and then so we'd write that as the x coordinate of an ordered pair, and then we would write down the range element that domain element arrived on campus, and that's the one that person gets assigned to. So like I would get assigned to Subaru because I probably would have driven a Subaru into campus today. So some of you who are with me right now, and I'm going to flip the screen here. So some of you who are with me right now, I'm going to write my name down again, Jim and Subaru. Could you tell me the car that you would get assigned to? So Ashante, if you're listening, what make of car would you arrive on campus today, Ashante?
A Nissan.
Okay, there you go. Thank you. So Ashante would be the domain element, and Nissan would be the corresponding range element. Charlotte?
A Tesla.
Now, Charlotte, okay, so we're going to write Tesla. No one's ever told me that before. And so Charlotte's going to show off her Tesla sometime. We're all going to come onto campus and drive around in Charlotte's Tesla. So I think she's just making that up, but maybe not. I don't know. And then Cynthia? Say it louder, Cynthia.
A Jeep.
A Jeep. Okay, there you go. And Jennifer, we'll do one more. Jennifer, are you there? Let's let's make up a car for Jennifer. Let's say Nissan for Jennifer also. All right, and so we would continue to write this out, all the ordered pairs here. And so this set of ordered pairs would certainly be a relation, because remember, any set of oh, I got your message, Jennifer. So thank you for letting me know that. Any set of ordered pairs, remember, represents a relation. So this is certainly a relation. So the question is, does this rule constitute a function? Does this rule, which is a relation, because all rules like this are relations, does this rule, which is a relation, also constitute a function? Does it satisfy the definition for a function? Right, that's our question. So if you go back to the definition for for a function, you have to have every domain element that gets assigned to something. So we're going to assume in this case that everyone arrived on campus in a car. So if everyone arrived on campus in a car, every domain element gets assigned to something. So every domain is assigned to a range. In other words, everyone arrived in a car. By the way, if you hear snoring in the background as I'm lecturing and wonder what the heck that is, I do have two large labs in the room with me right now, and one of them in particular is snoring quite loud. And so if you hear some snoring, it is not me, and I'm fully engaged in the class, but my dogs, who are both in here asleep with as I'm lecturing, yeah, well, they may be making some noise sometimes. So. All right, so everyone arrived in a car. So every domain is assigned to something. So that condition is satisfied. And so that, now remember, there's one other condition that has to be satisfied, and that is that every domain has to correspond to exactly one range. Now this is something we need to look a little bit more carefully at. So every domain has to be assigned to one range. So first of all, don't let, for example, the fact that Ashante is assigned to Nissan and Jennifer is assigned to Nissan, don't let that mess you up. Nissan is written in there twice, but the question is everything assigned, every domain assigned to exactly one range? And so the question there is Ashante assigned to just one range? Yes, it's Nissan. Is Jennifer assigned to just one range? Yes, it's Nissan. Now, it happens to be the same range value, but the definition doesn't say anything about the fact that the range value has to be different. It doesn't have to be different by the definition. It just has to be one. So the next question here is there a domain? Is there any domain assigned to two ranges? Now, think about that physically in this problem, because the rule here was that everyone is assigned to the make of automobile that they arrived on campus in. Well, did anybody arrive in two cars? I mean, it's a goofy question, right? But we have two cars right next to each other, and you're laying in one car and in the other car at the same time as you're driving onto campus? Probably physically that didn't happen. So did anyone arrive in two cars? And I think the answer there is pretty clear. No, right? No way that happened. So what's true here? Did every domain get assigned to exactly one range? Absolutely, definitely. So this is true here. And so rule one is a function. Rule one is a function. Now notice that, and I wanted to purposely kind of go this direction. Notice we had at least one situation where a range value was repeated, where it repeated y values. And my guess is if we had written the entire class out, we would have had lots of repeats in there. And so notice that in this definition, what we could certainly write here is that repeated y values are okay. Repeated y values are okay when you have a function. That's not a problem, right? To have y values get repeated in a set of ordered pairs, right? So no problem with repeated y values here when you're talking about a function. All right, one other thing here is, as we're talking about this set of ordered pairs for Rule 1, is we can now use what's called function notation to write out this function if we want to. So we first name the function. So we name the rule or the function. Now in algebra, the most common letters you'll see are F, G, and H, but you can really use any letters you want as long as you're not using the domain value or the letter that you're using to represent the domain represent the function also. But as long as you're not doing that, then you could really use any letter you want to. I'll just use F or G or H because those are the most common ones. But so if we name the function in this case, and in this case we'll name it F, then what we could do is we could simply write out this kind of notation, that F of Jim is equal to Subaru, like that. And F of Ashante is equal to Nissan. And F of Charlotte, this is the exciting one, I guess, is equal to Tesla. Charlotte evidently drives a Tesla. Charlotte, we're going to demand pictures of you driving your Tesla for proof of this. All right, so, and then so on. Right, and so this is what we call function notation, where notice what you're writing here is you're writing that F of the domain value equals the corresponding range value. Or you could just simply write F of X is equal to Y. Right, and so this is a nice little way of writing out how a function relationship works and what the rule does to a particular domain value. So it's a really nice notation for that kind of thing, and we're going to use that notation heavily in class. All right, so before we do anything else with this, let's move on to Rule 2 here. So we're going to keep the same domain and range, so same domain, everybody in the class, and range, makes of car. And so what we want to do in this case is change the rule, though, and say that everyone is assigned to the make of car they own. All right, that you get assigned to the make of car that you own. So that does require a little bit of thought there, an explanation about how that works. But I want you to think about car ownership for a minute. You know, in the state of Texas, everyone is, you own your car if your name is on the title, right? Car ownership depends on your name being on the title. So some of you may have a car that you drive around a lot that you refer to as your car, but it really isn't your car. You know, it belongs to somebody else because somebody else's name is on the title to that car. So your name has to be on the title. So first of all, and I'm not going to list any names here or anything like that. But if there's a non-car owner out there, so let's pretend that Henry, and I don't have any Henrys in this class, I don't believe, so that's a safe name to use here. So let's pretend that Henry does not own a car. Right? So then what happens here in this particular relationship, you know, Henry doesn't have anybody that he's assigned to. Right? So if we tried to write the ordered pair out, we have Henry written there, and then there wouldn't be anything to assign to Henry at all. And so what we do here in a situation like this is we get around this. We have a domain value that's not assigned to a range value. We simply kick Henry out of the domain. So kick Henry out of the domain. Right, so we exclude Henry from the domain in a problem like this. So, this happens all the time in algebra where we have a domain value that doesn't get assigned to something and we're not sure whether that value is in the domain or not. We see it's not assigned to anything, so what do? We exclude it from the domain. So as an example here, let's just look at this equation, somewhat more traditional algebra example here. We have y equals 1 over x minus 3, right, where this equation tells us how the relationship works, how a domain is assigned to a range. So for example, and by the way, y, if we named this function, we could use function notation. We might name it f of x equals 1 over x minus 3. All right, remember f of x and y mean the same thing. The y value is what f is doing to the x value, right? So in this particular problem, if we chose, for example, choose a domain like x equals 4, then f of 4 would be 1 over 4 minus 3, or 1 over 1, or 1. Right? So we have that f of 4 is 1, and the ordered pair then that is part of this function would be the ordered pair 4, 1, right? That 4 is the domain value, 1 is the corresponding range value. All right, if we choose x to be, let's say, -2, and I am picking these domain values out of thin air here, by the way, so don't think that there's a particular reason why I'm choosing these values. So what does this function do with -2? Right, it would be 1 over -2 minus 3, or 1 over -5. And so we have that f of -2 is equal to -1/5, and the ordered pair would be -2, -1/5, like that. Right, and that would describe this relationship right here. Right, we continue to write these ordered pairs out, and that would be the relationship. So what happens when we choose x equals 3 for this function? Well, we have f of 3 is equal to 1 over 3 minus 3, which is 1 over 0. And don't tell me that 1 over 0 is 0, because it's not. Remember, 1 over 0 is undefined. Right? This is an undefined expression. It's a meaningless expression. So what happens? 3 does not get assigned to anything. Right? So 3, x equals 3 is not assigned to a range by f, by this rule, and the rule in this case is 1 over x minus 3. So what happens here? We throw 3 out of the domain. So we throw 3 out of the domain. We exclude it as a domain value in this case. Right? And this is what we've done with Henry now, because Henry's a non-car owner, so we throw Henry out of the domain. And we throw anybody else who's a non-car owner for rule 2, we throw them out of the domain. Right? So the question here is this rule 2, is rule 2 a function? So I'm going to write, is rule 2 a function? So we've kicked all the non-car owners out of the domain. That means we're only left with car owners, people who get assigned to something. So the first condition of the definition for a function gets met. So the question is, what about the second rule, or the second condition for a function? And the second condition is that every domain gets assigned to exactly one range. So in this case, I'm going to use myself as an example here. Remember that I own a Subaru. So Jim Subaru would be one of the ordered pairs in this relation, but another ordered pair that would be in this relation would be Jim Toyota. So I also own a Toyota. And so what do we have here is that we have one domain value that gets assigned to two different range values. That's a problem. So this is a problem right here. And why is it a problem? Because the definition for a function says that every domain can only be assigned to one range. But in this case, what happens? Jim is assigned to two ranges, right? Jim is assigned to two ranges, and that's a problem. And that would be probably true for other people who are listening right now, that there may be other people who have two vehicles that they would get assigned to here, two or more. And so that's a problem. That can't happen when you have a function. And so rule 2 is not a function here, right? So here I've got, is rule 2 a function? And the answer is no. Why not? Because you've got one domain is assigned to two ranges, right? And so when we go back to our definition here, where I've got repeated y values are okay, right underneath that I'm going to write repeated x values are not okay, right? That if you have repeated x values, you don't have a function, right? And so that's important that you know that as you go through the rest of the semester. The repeated x values are a problem, okay? All right, so rule 2 is not a function, right? So we've looked at two rules associated with that domain and range, and so now what we're going to do is we're going to look at maybe somewhat more traditional sets of ordered pairs to see whether these satisfy the definition for a function. So let's just start with some actual sets of ordered pairs. So let's say I have 3, 6, and 4, 8, and 5, 10, and let's say I also have negative 5, 10. So let's say that that's our set of ordered pairs. So is this a function or not a function? That's our question here. So I put function down, but I put a question mark. It is certainly a relation. The question is, does this definition satisfy the conditions that need to be met for it to be a function? And really all we need to do, if you think about this, is we need to go back to our definition here and look to see if we have any repeated x values. If we don't have any repeated x values, then what we're looking at has got to be a function. Remember, repeated y values are not a problem. It's repeated x values that are the issue. And in this particular relation that I've got written here, right, the domain or the x values are 3, 4, 5, and negative 5, and the range is 6, 8, 10, and we wouldn't write 10 down twice. And there are no repeated x's. We have some repeated y's, that's not a problem, but no repeated x's. So is it a function? Yes, this is a function. That's all you have to look at. We could name this function. I could name it g. And if I name it g, then we could say that g of 3 was equal to 6 because of the ordered pair 3, 6. Remember that 3 is the x value and g of 3 is equal to a y value. G of 4 would be equal to 8 because of the ordered pair 4, 8. G of 5 would be 10 because of the ordered pair 5, 10. And g of negative 5 would be 10 also because of the ordered pair negative 5, 10. Like that. Right, so we could use function notation for that set. All right, let's name this next relation. So let's look at another set of ordered pairs. So we have 0, 0, 0, 0 is an ordered pair, and 1, 1 is an ordered pair, and negative 1, 1 is an ordered pair, and 2, 4 is an ordered pair, and negative 2, 4 is an ordered pair. And let's say I've got 1, negative 1, and negative 1, negative 1 also. Right, so a lengthy set of ordered pairs here maybe. The domain The set of x values would be 0, 1 and negative 1, 2 and negative 2. The range would be 0, 1, 4, and negative 1. Is this a function or not a function? And the answer here would be clearly not a function, right? Because what do we have here? We have repeated x values. We have repeated x values. And when I say repeated x values, I'm saying that I've got the ordered pair 1, 1 in there, and I've also got the ordered pair 1, negative 1. Right, so what do we have here? That 1, which is a domain, gets assigned to 2 different ranges. That's a problem, right? And negative 1 is the same thing. We have negative 1, 1, and we have negative 1, negative 1. And so you have one domain that gets assigned to 2 different ranges. That's a problem, right? Can't have that happen if you have a function. And so is this a function? No, this is not a function. It is a relation. Remember, all ordered pairs, all sets of ordered pairs are relations, but it's just not a function. All right, so we've got a couple of sets of ordered pairs written down, decided whether those are functions or not. So now let's look at some graphs. Another way that we would see a set of ordered pairs written out. So in this case, let's look at this particular relation. Remember, all sets of ordered pairs, so that means any graph I sketch is automatically a relation. So let's look at this relation like this and like this. So this is our relation right here. This is the picture of the set of ordered pairs. And there's an infinite set of ordered pairs on here. And we could write the domain and the range for the graph with no problem. Remember, and so let's do that in this problem just to practice that, because we definitely want to practice that. So the domain in this case, remember you're walking along the x-axis and you're looking to see where you see the graph and where you don't, and you're walking from left to right, always, 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 always from left to right. So the first place you see the graph is here at 2. And then notice you see the graph after 2. You see it always because there's arrows at the ends of those 2 pieces of the graph. And those arrows mean the graph just continue on forever. So as you're moving off to the right from 2, right, you continue to see the graph. So this person standing right here, wherever that value is, definitely sees the graph. It's just up, pretty far up and pretty far down right there. And so the domain in this case starts here at 2, but it goes on forever to the right, and so it'd be 2 to infinity. That would be our domain. And then the range, remember you're now climbing up the y-axis, and you're going from bottom to top. Notice in this case, the range, it doesn't matter where this person is located on the y-axis, they always see the graph. No matter, even a person who's sitting down here, way down below what I've got pictured right here, this person still sees the graph over here because those arrows mean that the graph continues on forever. And so the range in this case is every real number. No matter where you are on the y-axis, you always see the graph, and so the range would be negative infinity to infinity. In other words, all reals. Every real number is in the range. So I'll say all reals, or you might actually also say the entire y-axis. Right, every y value on that y-axis is part of the range right here. All right, so we've got the domain and the range written down. So now the question is, does this particular graph, this particular set of ordered pairs, satisfy the definition for a function? And it doesn't, does it? Because so for example, I could pick this y value, this x value of 5, and I notice that I've got 2 different ordered pairs here that have that x value of 5. I've got 5, 3 right here and 5, negative 3. And so notice we have repeated x values on this graph. So repeated x values on the graph. And so this is not a function. Now notice when the repeated x values occur, one way we could look at that is we could say, kind of go along these lines, that, hey, if I draw a vertical line through the graph, if I can get a vertical line that intersects the graph twice, then it is not a function. And if I can't do that, then there are no repeated x values and the graph would be a function. This is sometimes called the vertical line test. And the vertical line test is a nice, easy way of deciding whether a graph represents or just a relation, or if the graph represents a function. If you cannot draw a vertical line that intersects the graph more than once, if you cannot do that, right? If you cannot draw a graph like that, or a vertical line like that, then the graph is a function, right? It represents a function. If you can draw a vertical line, and I'm not going to write the whole statement down here, but if you can draw a vertical line that intersects the graph more than once, then the graph is not a function. And this is called the vertical line test. And so this vertical line test is a nice way to always be able to look at a graph and immediately say whether that graph represents a function or does not represent a function. So let's look at some graphs here. Let's write down domains and ranges. Remember, you can write the domain and the range down no matter what the graph looks like, whether it's a function or not a function. But we also then want to talk about the vertical line test and whether the graph actually represents a function. So let's write down domain and range and then whether the graph represents a function or not. All right, so let's look at this graph right here. Let's say that it starts here at -3, -1, goes through that point, and then it comes up to the y-axis right here at 0, 2, and then this graph comes down this way, like so, and it passes through the point 2, 0, and then finishes over here at 5, -3, like so. All right, so let's first of all write down the domain and the range for this graph. This does represent a set of ordered pairs. So as I'm moving along the x-axis in this case, right, as I'm walking along the x-axis, I first start seeing the graph here at -3. And so I would, and -3 is actually part of the graph, so I'd write -3 with a bracket. And then as I move along the x-axis, I see the graph for every x value until I get to 5. And so the domain would be from -3 to 5. And then the range on this graph is I'm climbing up the y-axis, right, from bottom to top. The first place I see the graph is here at -3, right there. And so the range also starts at -3. And then the range, I continue to see the graph. No, sometimes I see the graph twice. Sometimes I just see it once as I'm looking left and right. That doesn't matter. As long as you see it, left or right, that's all that matters. So the last y value where you see the graph is at 2. And so the range would be from -3 to 2. Something else I'd like you to be able to read off of the graph is I'd like you to be able to read the intercepts for the graph. We need to start talking about that. So the intercepts for this graph would be the x-intercepts, remember, are the places where the graph crosses the x-axis. And so the x-intercepts would be here at 2, 0, and then another one here at -2, 0. So there's 2 x-intercepts. And then the y-intercept, the graph crosses the y-axis at the point 0, 2. Notice that x-intercepts always have a y-coordinate of 0, and y-intercepts always have an x-coordinate of 0. That will always be true. So now the next question, does it represent a function? So I put function, I put a question mark there, and the answer here is yes, it does represent a function. It passes the vertical line test. So it passes the vertical line test. I will abbreviate vertical line test just with the letters VLT during the semester. And so since it passes the vertical line test, in other words, every vertical line I draw only intersects the graph once, right? Most once. And so this is a function. So yes, it is a function. Function notation. Let's look at function notation with this graph. So lots of things going on with the graph that we want to be talking about. So function notation goes like this for a problem like this one. If I write f of 4, for example, then what I'm telling you to do when I write f of 4 is I'm saying look at where x is equal to 4 and see what the y value has to be. So in our graph, x is 4 right here, and the y value, we go to the graph, and the y value is at -2. And so f of 4 is equal to -2. And you might write that 4, -2 is on the graph. That's what you're looking at here. All right, so if we continue that with function notation on this problem, now function notation we would not use if the graph was not a function, right? If it fails the vertical line test, we would not be doing this last part. So f of -1, here's -1 on the x-axis, and then I go up to the graph here, and I get that the y value is 1. And so we say f of -1 is equal to 1. The point -1, 1 is on the graph. So I certainly would want you to be able to pick off function values off of a graph also, if the graph actually does represent a function. All right, let's move on to let's look at a couple more examples like that.
So I have a quick question.
You bet. Ashante, yes ma'am.
When you would give an exam, which answer or which specific notation would you be looking for? Would it be just a function? Would it be the function notation?
You'll know by the problem. So like let me show you a typical test question would go like this. And let's go ahead and do this problem here. So typical test questions. That's a good question because you want to know how I'm going to ask things certainly on the test. I definitely agree with that. So let's look at this graph. Let's say we have maybe a slightly more complicated graph than what I just had, possibly. Let's say that I have, excuse me, a graph that looks like this one. Oh, let's say it looks, starts here at that point, which is at -2, 3, comes down like this, and let's say we have this graph like this. All right, this is the graph we're going to be looking at. So this would be I might have a test question like this. So I would give you a graph, and the first thing I would say is function or not a function. And so I might actually say in words, is this a function? Does this graph represent a function? Or I just might put function with a question mark there. And in this case, it'd be a yes or no answer, but it would be based on the vertical line test. And so in this case, this graph, yes, does represent a function because the graph passes the vertical line test, right? Graph passes the vertical line test. In other words, every vertical line I draw only intersects the graph once. The next thing I'm going to ask you to do is I'm going to ask you to write down the domain for the graph. And by the way, let's name this graph G, like that. So I might ask you to write down, or I definitely will ask you to write down the domain, right? So as you're moving from left to right on the graph, the domain is the set of x values, right? So remember, you're walking from left to right on the x-axis. And so the first place you see the graph is here at -2, right? You see the graph right there at -2. And then after -2, you actually see the graph forever after that as you move along the x-axis because there's that arrow on the graph, which means this graph continues to go like it's been going, and so it will continue to spread out forever. And so the domain would be bracket -2 to infinity. The range, as you're climbing up the y-axis here, right? Climbing up the y-axis, right? The first place you see the graph as you're going from bottom to top is you'll see it here at 0, right? At 0, you start seeing the graph, and then you see the graph forever after that, right? As you draw a horizontal line, sometimes you see the graph twice, sometimes you see it just once, but you always see the graph because of that arrow. And so the range here would be from 0 to infinity. So I'll definitely ask you for the domain. So I'll ask you for sure whether the graph represents a function. I'll ask you for the domain of the graph and the range of the graph. I will ask you for the x-intercepts and the y-intercepts for the graph. I'll just say, what are the x-intercepts for the graph? Where does it cross the x-axis? And in this case, the graph crosses the x-axis at the origin at 0, 0. And so that's the x-intercept. It doesn't cross the x-axis anywhere else. And then the y-intercept, well, it also crosses the y-axis at 0, 0. And so that would also be the y-intercept. And then the last thing I would ask you as of right now, from what we've talked about, is I'd ask you to evaluate some function notation. So I might just say, what is g of 2 in this function? Right, so I put g of 2 written down here like this equals, and I'd ask you to fill it in. So at g of 2 in this problem, right, we go to where x is 2, which is right here. We see that when x is 2, we get that ordered pair, which is 2, 3. And so g of 2 is equal to 3. Right, and that's what I'd ask you to fill in right there. Let's see, g of -1. So we go to where x is -1 on the graph, and when x is -1, which is right here, we get that the y value is 1. And so g of -1 is equal to 1 in this graph. You know, so Shante, this is exactly kind of thing I would be doing here, is I'd just be asking you some specific things about the specific graph we're talking about. And it's kind of, in some ways, like you're filling in the blank with the answers. You're reading the information from the graph. So function, basically that would be yes or no. Domain and range would be interval notation that you would typically write out. X-intercepts and y-intercept would be ordered pairs that you'd be writing out. And then function notation, you'd just be answering with values, with y values, right? These are all y values right here. And so those would be the kinds of answers you'd be giving for these kinds of problems. So Shante, hopefully I've addressed your question. Have I addressed your question here?
Yes, you have. Thank you so much.
Okay, you're welcome. Definitely. Thank you for the question, too. That was a good question to kind of go back over some of that. So, all right, so let's look at this graph. Next graph here. So on this next graph, let's see. So let's say I have the graph looks like this. Right, so it's a parabola that opens off to the side here. So first question here on this graph is this graph represent a function? And the answer here would be definitely no, right? This graph fails the vertical line test. And so that means I can draw a vertical line that intersects this graph more than one time. And because I can do that, so like right here, I'm drawing a vertical line that intersects it twice. And because it intersects twice, I have two ordered pairs there that have the same x value. 1, 2, 3, 4, 5, 6. Those have the x value 7 in both cases, but they have different y values. It's 7, 2 and 7, -2. And so what happens here, 7 is taken to two different y values. 7's an x value, it's a domain value. It gets taken to two different ranges. That's a problem. You can't have that happen. All right, so this fails the vertical line test, so not a function. Now, just because it's not a function doesn't mean I'm not going to ask you for the domain and the range, because the domain and the range is simply the set of x and y values. So the domain here, as we're moving along the x-axis, the first place we see the graph is at 3, and we see it forever after that, and so the domain would be from 3 to infinity. The range, on the other hand, because you have to be careful here, the graph has arrows at the end, and because it has arrows, it means the graph continues to spread out forever, right? And so this is going to spread out like this forever and spread out like this forever. And so the range, literally, no matter what y value I'm looking at, I will always see the graph. And so the range is going to be from negative infinity to infinity. All right, so that's the domain and the range for this graph. The x-intercept, I could certainly ask you that. The place where the graph crosses the x-axis, and that's a pretty clear cut there, is that's that point 3, 0. The y-intercept, if you look at the graph, this graph never crosses the y-axis, and so I would write none. So I could ask you for the y-intercept here, but you just simply tell me it doesn't cross the y-axis at all. And then there would be no function notation questions here because it's not a function. So since it's not a function, we do not use function notation. So no function notation questions. So no function notation questions here. All right, so let's see, a couple of more things to deal with here. Let's look at another graph. So this graph is going to be a little bit more complicated. So let's say that, now I'm putting these dashed lines here, and I'm going to explain these dashed lines in a minute. This is not part of the graph. This is just some things we need to know about the graph. And so let's say the graph looks like this. The graph's in blue. And the graph kind of fits in between these dashed lines that I've got drawn here, like this. All right, so these dashed lines are called asymptotes. These are called asymptotes. And we are going to encounter graphs with asymptotes frequently during the semester. The vertical line, which is at when x is equal to 3 here, is called a vertical asymptote. And that vertical asymptote occurs in this problem. If you just look at the x-axis, if you look at every x value on that vertical line, I want you to think about every x value in that vertical line is 3. And so the vertical asymptote is at x equals 3. And then this vertical line is called a horizontal asymptote. And these asymptotes, and by the way, the horizontal asymptote occurs in this case when y is equal to 1. If you look at every y coordinate on that horizontal line, they're always equal to 1. So we say the horizontal asymptote's at y equals 1. These are lines that the graph approaches. Lines the graph approaches, but typically does not cross. Now, vertical asymptotes, we will find the graph literally never crosses the vertical asymptote. Horizontal asymptotes, as it turns out, sometimes when an equation has a graph that's got a horizontal asymptote, it actually does cross the horizontal asymptote. The graph does, but that's much later in the semester. Don't worry about that now. So we're just going to assume that these are two lines that the graph approaches, but never actually gets to them. So this makes the domain and the range trickier. First of all, function. Is this graph a function? That's our first question. And the answer here would be yes, it passes the vertical line test. You can't draw a vertical line that intersects the graph more than one time. And so this graph does represent a function. So the domain on this graph, a little bit trickier than what we've been writing. Now think about this as this person is walking along the x-axis right here. You know, they're walking along. They see the graph for all these vertical lines I'm drawing right here. See the graph, see the graph. But at x equals 3, that vertical line right there, remember, is a vertical line that the graph does not cross right here at 3. And so 3 is not in the domain. So I'm going to write that in words here. 3 is not in the domain, and it's because there's a vertical asymptote at 3. at x equals 3 right there. And then as you proceed on past 3, then you can start seeing the graph again. Right? And so the domain on this in words is everything but 3, every x except 3. And so the way we write that in interval notation is we say negative infinity to 3, but we put a parenthesis around the 3, and then we need another set, and we started at 3 again, another parenthesis at the 3, and then go to infinity. And so that's the way you write out the set that's every x value except x equals 3. It's all the x values less than 3 and all the x values greater than 3. And so that's the domain. With the range, we've got exactly the same thing happening with the y values, but this time is at 1. So we say that 1 is, I guess maybe I'll put this in a different color here. We say that 1 is not in the range, and that's because of the horizontal asymptote there. At y equals 1, like that. And so the range would be everything but 1. So we'd say negative infinity to 1, union 1 to infinity. And notice we put parentheses around the 1. And that's every y except 1. All right, so that's a little bit more about that graph. So, and then let's say x-intercepts. I still would ask you for the x-intercepts also. And this graph crosses the x-axis at the point 2, 0. And so that would be an x-intercept. The y-intercept, the best you could do here is estimate it because of the way I drew the graph. It's where the graph crosses the y-axis, and the y-intercept is this point right in there. And so we'd say 0 and maybe like something like 0.8 is an approximation for the y-intercept right there. Right, so I could say 0 and then the y value would be 0.8. That would be an approximation for it. All right, one last thing we need to talk about before we'll shut down the, let's just talk a little bit more about function notation to finish this. Now, frequently, instead of a graph, you're going to be given an equation. So like, for example, you might be given the equation f of x equals 2x plus 3. Remember, this is just another way of writing y equals 2x plus 3. Well, what have we done? We've named the function. We've used some function notation there to write it out. We've named the function f. And we could evaluate function notation numerically on a problem like this pretty easily. So like f of 2 would simply be substituting 2 in place of x, because you're saying that x is equal to 2. And so you're literally just plopping 2 in for x there and getting 7. So f of 2 is equal to 7 in this, for this equation, this function, or it goes through, if we look at the graph, the graph goes through the point 2, 7. All right, f of negative 5 would be 2 times negative 5 plus 3, or negative 10 plus 3, or negative 7. So you'd have f of negative 5 is equal to negative 7, and it means that the graph goes through the point negative 5, negative 7. Now I'm just picking these x values, by the way, out of thin air here. So sometimes you'll see things like this, and this is actually going to be important for us, and you'll see why as we go through the semester, but like f of t, you wouldn't do anything different. Every place you see an x, you'd substitute t. You get 2t plus 3. Now, there would be no arithmetic you could do there. You just write 2t plus 3. So f of t is equal to 2t plus 3. And as an ordered pair, you could definitely write this, that the x value is t and the y value is 2t plus 3. That would be okay to write. If we had f of negative x, f of negative x, every place you see an x, you'd substitute negative x. So you have 2 times negative x plus 3, or that would be negative 2x plus 3. Right? And that would be okay to do. The x value would be negative x, and the y value would be negative 2x plus 3. You don't usually see that written out as an ordered pair, but you could do that. f of 3x. Every place you see an x, right? Every one of these problems, what did I do? I wrote down the function, and in place of the x, I wrote down the given domain value for the function statement. Right, so notice in every one of these problems, I started out by writing out 2x plus 3 each time. Right, here's 2x plus 3. Here's 2x plus 3. Here's 2x plus 3. Here's 2x plus 3. Every time, I'd write out 2x plus 3, but in place of the x, I would put the domain value that I'm being told to use in the function statement. So this problem, f of 3x, I'd get 6x plus 3. And so the domain value would be 3x, and the range value would be 6x plus 3. All right, so I wanted to write that down so you had a little bit of that to fall back on also. So let me look at some textbook practice here. Textbook practice for you, and then see if there's any quick questions here at the end, and then we will be done for the day. We have a lot to do with functions this week for sure. So section 3.1, we are over on page 176 in your book, and this would be problems 27, 29, 35, 37, 39. And then 41 through 51, odd. That's practice with the vertical line test. And then, actually I should have said 53 there at the end, so that's 53. And then that's it for that group of problems. And then in section 3.2, and we're not done with either of these sections, by the way. There's some things in both sections that we still haven't done yet. But in section 3.2, this is page 193, problems 27 through 37 odd. And we still have more to do in both of those sections also. All right, does anybody who's still with me here, did anybody have any questions that they need to ask before we shut down for the day?
No, I'm good.
I'm good. I don't think so.
All right, don't hesitate to come by my online office for help. Don't hesitate to send me a remind message if you have a question. Don't hesitate to send me a WebAssign question. You have lots of ways to get in touch with me and get questions answered. So everybody have a great week, and look for the Exam 1 review later today, as well as the solutions to the practice problems on inequalities. Have a wonderful day.